Today we're going to look at the pH of weak acids. So a quick reminder about what a weak acid is before we start to figure out how to work out its pH. A weak acid is one of those acids where the H plus ion only partially dissociates. In fact, it is not in concentration equal to the concentration of the acid that produced it, because only some of those molecules have given over their H plus ions. There is in fact an equilibrium, and you can see there that this particular acid is in equilibrium with H plus and the other part, the A minus part of the acid. So with these, there is always some hydrogens coming into solution and always some hydrogens recombining and going back out of solution, rejoining in with the original acid. Now here are some common examples. You will have heard of some of these: ethanoic acid, what used to be called acetic acid, CH3COOH, it's like vinegar and things like that. Carbonic acid, H2CO3, citric acid found in lemon juice, and phosphoric acid. That was that tribasic one where basically all three hydrogens would be removed or dissociate, but with ever increasing dissociation constants. So for all intents and purposes, that first H plus is removed like a weak acid. So in order to process and find the pH of a weak acid, we need two things. We need the concentration of the acid to start with, and we also need the acid dissociation constant, Ka. Now I'm going to show you how to calculate Ka using values that you're going to be given in the question. So if you remember what Ka was, as we spoke about it before, it was like an equilibrium constant, like Kc. Tells us about whether or not the reaction is more strongly to the right or to the left. And it's found by multiplying together the concentrations of the products and dividing it by the concentration of the reactants. And that ratio tells us whether or not this reaction is producing more of the product or there are more reactants. It's happening faster backwards. So in an acid, in this dissociation, and recalling the equilibrium equation on the previous slide, where it was the acid on the left and it was turning into H plus and A minus on the right. Well, we need to take the concentrations of H plus and A minus and multiply them together. Now, what we're going to say is we're very specifically referring to when these were in equilibrium, because that is what Ka ultimately defines when it has reached its equilibrium position. And we're going to divide that by the concentration of the reactants. In this case, it was a single reactant. It was the acid that was being dissociated. And so we subscript all three of these values with equilibrium. But we don't always know the concentration of the acid when it is in equilibrium. But what we do normally know is what the concentration of the acid was at the start. And so we can actually realize that if we took away from the concentration of the acid at the start, however many hydrogens have left it, that would tell us what the concentration was at the equilibrium point. So think about that one more time. We know the concentration at the start, a bunch of H plus has left, and now whatever remains is the concentration of the acid at equilibrium. So we're looking at what has not lost H plus, because everything that has lost H plus has now turned into an A minus. Everything that has not dissociated, the HA at equilibrium, we just take the starting concentration and subtract however many hydrogens have left, have dissociated. And we can substitute that into our formula. We change the denominator line, substituting in the place of HA, concentration of HA in equilibrium, with the concentration of HA at the start minus the concentration of the H plus ion. This is quite complicated, but what we can do is introduce two approximations, which makes it really quite simple. And those approximations are valid for weak acids, and it means that the calculations that we do correctly represent what's going on. So the very first approximation is based around the idea that for every H plus ion that you create, it's going to have to have separated from the other half of the acid, the A minus. And so the concentration of one is always going to be equal to the concentration of the other. They're going to be produced in pairs. Now, the second approximation is that considering that this is a weak acid and it is a very small number of the H plus that actually does dissociate, it's so infinitesimally small compared to the concentration of the acid to start with, that really the change in concentration of the acid to start with is negligible compared to its value. Compared to the size of the number, its change is very tiny. It means that we can approximate that the concentration of the acid at equilibrium was pretty much the same as the concentration of the acid to start with. Now, these two approximations, they are going to find their limits. We're going to find places where they are no longer valid, but for now, we're going to apply them and see how this simplifies our calculations to find the pH of the weak acid. So going back to our formula for the acid dissociation constant, found 2 slides ago, we can actually substitute in those approximations. So on the top line, look at the numerator. The concentration of the H plus ion in equilibrium multiplied by the concentration of the A minus ion in equilibrium. Now what we've said is that these are equal to the same. So essentially it's like multiplying a number by itself. They're both equal to the concentration of the H plus ion. And so we can replace the numerator line with the concentration of the H plus ion in solution in equilibrium squared. And that simplifies the top line. It means that it's dependent only on the concentration of the H plus ion. On the denominator line, what we said is that the concentration of the acid to start with minus the very, very tiny concentration of the H plus ion is essentially going to remain unchanged. It's going to stay as the concentration of the acid to start with. And so the acid dissociation constant Ka can be written as the concentration of the H plus ion squared divided by the concentration of the acid at the start of the reaction. And now these are things that we could know. It's now narrowed down to a small number of variables, and we can compute some answers using these. We only need the concentration of the H plus ion that we could find through the pH of the liquid, for example, the acid dissociation constant, or the concentration to start with to work out the third quantity. It simply becomes a 3-variable problem. So if you could know the concentration of the H plus ion from the pH, what you could do is you could substitute it into this formula. So this is just a rearrangement to make it in terms of the pH. So here it's in terms of the concentration of the H plus ion, which of course we can compute further to find the pH. But it's equal to the square root of the acid dissociation constant multiplied by the concentration of the acid to start with. So here is a worked example. Calculate the pH of 0.0245 moles per decimeter cubed ethanoic acid, CH3COOH, at 25 degrees C, where Ka is equal to 1.7 times 10 to the minus 5 moles per decimeter. So we have calculate the pH. So the ethanoic acid, so the first number there, 0.0245, that is the concentration of the acid to start with, HA. And also, we've got the acid dissociation constant, and it wants us to find out the remaining thing, which is the pH. So first of all, we need to write down that formula we used before. Apply the approximations basically means we take the simplified version of that formula, that the concentration of the H plus ion was equal to the square root of Ka multiplied by the concentration of the acid to start with. And then substituting in those numbers, as we'll see on the next page, we can then progress to find the concentration of the H plus ion and then the pH of the acid. So here is the application of those approximations. We're saying the dissociation is very small. We're saying that the amount of A minus is approximately equal to the amount of H plus. And so therefore we get this formula that the Ka is equal to the x squared. In this case, x is the concentration of the H plus ion squared divided by the concentration of the acid to start with. So getting to our starting equation, you won't need to do this in the exam. You won't need to explicitly write down which approximations you are applying unless it asks for them. And so now it's just about rearranging that formula and solving for the concentration of the H plus ions. So what we can see is that the concentration of H plus ions is equal to the square root of the acid dissociation constant times the concentration of the acid to start with. We put those numbers in, use our calculator, and we get this as a 0.0000645 moles per decimeter cubed. This is the concentration of the H plus ion. And what we can, of course, do is substitute that straight into the equation for pH. pH is negative log to the base 10 of the concentration of the H plus ion. And so we substitute that number that we just found, 0.0000645, and we calculate that the pH is equal to 3.19. And so that is the pH of this ethanoic acid. It's a simple calculation, so expect to do it in the exam. A question might ask us to calculate the acid dissociation constant of a weak acid, or indeed, we might be asked to do this in a practical activity. So one of the things we'd need to know to calculate Ka is the concentration to start with. We'd also need to know the pH, and then we would be able to work out what the acid dissociation constant was. So we'd measure the pH accurately with a pH meter. Here's one here, but others are available. And we need to kind of do the previous method backwards. So if we know the concentration of this propanoic acid, and if we know it is 3.04 from measurement, then what we can do is we can use the formula to work out, first of all, from the pH, what the concentration of the H plus ion is, and then by writing out the formula for the dissociation constant, we can work out that. So let's have a look at a workthrough of this. So first things first, we need to substitute in, we need to rearrange the equation for the pH in terms of the concentration of the H plus ion is equal to 10 to the power of negative pH, and so that was 10 to the power of minus 3.04. Put it into our calculator, we get an answer of 9.12 times 10 to the minus 4 moles per decimeter cubed. That is the concentration of H plus ions in this propanoic acid. Now, it is right that we can apply those approximations in this situation. A key thing is that it suggested that it was at 25 degrees, and that is one of the conditions for these approximations to occur. Because Ka is dependent on temperature, we're going to say that this is true and valid and relevant only when the temperature is 25 degrees C. So here it is then, that Ka is equal to the concentration of H plus multiplied by the concentration of A minus. And so what we can do is we can substitute in these values. We've said that the concentration of A minus is the same as the concentration of H plus. We calculated that from pH in the previous step, and we can divide it by the concentration of the acid. Now what we're actually saying is that the concentration of the acid is going to be basically the concentration to begin with, and what we've left in this step is we've removed the concentration of the H plus. But actually, the concentration of the H plus, the 9.12 times 10 to the minus 4, is so small compared to the concentration of the acid to start with. If you didn't do that step, you would still come out with the same answer to 2 decimal places. So you can pick and choose whether or not you want to do that in this particular example. So here, we're simply calculating what the numerator and the denominator are in this fraction, and this gives us the value of the acid dissociation constant. It comes out as 1.3 times 10 to the minus 5. And that's the answer. Remember the unit, this is moles per decimeter cubed. So why is this a method for working out the pH that can only be used for weak acids? Well, it's because of those 2 approximations. If we go to very weak acids, those acids that are pH 6 or greater, so basically things that are acting as acids but generally at the neutral point or higher on the pH scale, then what we find is that something else we're going to talk about down the line is that water starts to dissociate. Some of the H pluses become separate from OH minus. It from the H2O, and they actually play a contributing part in the pH of these very weak acids. It becomes that there might be a higher concentration of H plus than there has been the concentration of A minus at in very weak acids and higher pHs. The second approximation is why it doesn't work for strong acids. It's because we've made this assumption that the concentration of the acid in equilibrium is the same as the concentration of the acid to start with. In a strong acid, so many of those acids can dissociate that this is no longer true, that the concentration of the acid in equilibrium is far, far smaller than the concentration of the acid to start with. This only works when the dissociation is tiny in comparison to the starting concentration of the acid.